Okay, so we're going to look at how we can calculate lattice enthalpies. And a lattice enthalpy can be defined as either an enthalpy of lattice dissociation or an enthalpy of lattice formation. Now, because we're thinking about lattices, this only works for ionic compounds. And in order to do this, we have to use a Haber cycle, which is quite similar to a Hess cycle, which we were looking at in year 12, but a little bit more complicated because we have to use the enthalpy of formation data, enthalpy of ionization energy data, enthalpy of atomization, bond enthalpies, and electron affinity enthalpies. So make sure you have read through the different definitions on the handout before you watch the video. So we're going to start with the example of sodium chloride. The idea being that we can use the enthalpy of formation of sodium chloride, and the equation for that would be sodium in its standard state plus chlorine in its standard state will produce sodium chloride. Now, because we have an enthalpy of formation, and we know that standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements, we cannot balance this by putting 2's in front of the NaCl. The way to balance this, we must put a half in front of the Cl2. So, now that we have that, we can start to think about the different steps involved in this reaction. Now, we'll start off with then thinking about the enthalpy of atomization. So the very first thing that must happen in this reaction for it to work is for us to have this sodium as a gas. So step 1 is going to be taking the sodium as a solid and turning it into sodium as a gas. Now that enthalpy change would be known as the standard enthalpy of atomization. So if we just put B delta H with a subscript AT, and then because it's a standard, we've got our symbol there as well. Now this enthalpy change will have a value, and I'm going to put this in as I go. It's 107 kilojoules per mole. Now, the standard enthalpy of atomization is the enthalpy change that accompanies the formation of 1 mole of gaseous atoms from the element in its standard state under standard conditions. So basically all we've done here is change our sodium from a solid to a gas. The next thing then, we need to change this sodium in its gaseous state into a sodium ion. So equation 2 is going to be taking sodium as a gas and turning it into sodium ions, still as a gas, and an electron. Now this is the enthalpy of ionization. The symbol will be delta H with a lowercase I, and in this case has a value of plus 496 kilojoules per mole. Now the idea is that the ionization enthalpy is the standard enthalpy change when 1 mole of gaseous atoms is converted into 1 mole of gaseous ions. Now here we've only got a single positive charge. We can have a second enthalpy of ionization, but in this case we don't need that. The next step then is thinking about the chlorine, because we want half a chlorine molecule, or we want a lone chlorine atom. Now, in order to do that, we need to think about the atomization of chlorine. Now, atomization is the enthalpy change which accompanies the formation of 1 mole atomization. Now, because we've already got, my apologies, missed a step there. Because we've got the chlorine already as a gas, we don't need to worry about changing the state here. But what we do need to worry about is going from Cl2 into Cl atoms. So the step here, we're going to be thinking about the bond dissociation enthalpy. It's easy for you to say, also known as the mean bond enthalpy. And it's the enthalpy change that involves breaking a covalent bond in a mole of gaseous molecules to form 2 free radicals that are also in the gaseous phase. So in this case, we'd have a Cl2 that would turn into 2 Cl atoms, all in the gaseous state, or we can write this as half a Cl2 in the gaseous state, which forms 1 Cl in the gaseous state. Now this is important because actually we'll have two different values here, and it's when we come to look at a question, look at the data that we're given, we have to make sure we account for this. So if we're given a value for the bond dissociation enthalpy, in this case we'd be given a value of, is the enthalpy of dissociation, be given a value of plus 2 for 2 kilojoules per mole. That wouldn't have the same value as this one, because this one would have a value of half of 242. So it's important that when we're given a question, we look at the actual information we've been given there. So we're going to continue with this one. We've got Cl2 turning into 2 Cls. Now that we've got our Cl as a lone atom, so we've got Cl in the gaseous state, we actually want to convert that into Cl minus. Now we refer to that as the electron affinity. Now the electron affinity is the standard enthalpy change when 1 mole of gaseous atoms is converted to a mole of gaseous ions that have a negative charge. So electron affinity only works to produce negative ions. So Cl will gain an electron to form Cl minus in the gaseous state. The value for this being, if I write my symbol, so we've got the enthalpy change of electron affinity, which will equal minus 349 kilojoules per mole. So we're now at a point where our final step, oh, a bit dodgy there, our final step is going to be taking our sodium positive ion, excuse me, and taking our chlorine negative ion and combining those two together. So we've got sodium plus in the gaseous state plus chlorine minus in the gaseous state, which will come together to form our sodium chloride in the solid state. Now this final step would be the lattice enthalpy. Now for us then, we have to be able to use all this information to work out that final value. Or we can go the other way and work out this value. Now, I'm going to give you this value. So sodium solid plus a half a chlorine gas produces sodium chloride, and the enthalpy change for that is minus 411 kilojoules per mole. So if I give you that value, we should be able to work out this value. Now, the way that we're going to do that then is set this out as a Born-Haber cycle. Now, the Born-Haber cycle allows us to work out any of these individual values as long as we have all of the others. And there are some tricks, well, not tricks, but some tips to follow to make sure we set this out in the right way. Now, you'll have noticed that for each of these points, I have made sure that I've put the state symbols each time. Now, remembering to do that is going to help us when it comes to putting this into our Born-Haber cycle and doing our calculations. Now, our final product in this reaction is sodium chloride, solid. So when I draw my Born-Haber cycle, I'm going to give myself a big chunk of space. You want about half a page here. You don't want it all crammed together in the smallest amount of space so you can't follow the numbers. So I'm going to start at the bottom and I'm going to put my NaCl solid. Now that's my end point. That's what I want to end up with. Now, the first thing I'm going to put on here then is my first step, so my actual equation, so this bit, my sodium solid and my chlorine producing NaCl. So that's going to go just above my final product, because what I've got here is sodium solid plus half a chlorine gas will produce sodium chloride. So notice how my arrow points from my reactants to my product, and that I've got my state symbols in there as well. This is an enthalpy of formation, so I'm going to put that on my diagram. It has a value of minus 411 kilojoules per mole. Now, the idea being then that I should be able to put together a cycle on here that allows me to work out any missing gaps on there. So, looking at my steps then, to get from this to this, the first thing I have to do is change my solid sodium into gaseous sodium. So, going back to my Haber cycle, I'm going to draw an arrow up to the next level. Now, it doesn't matter how big your lines are, how big your gaps are, as long as your arrows point in the right direction. So I'm now going to go from solid sodium to gaseous sodium, and I've still got my half Cl2 as a gas. Now, this step then was the enthalpy of atomization. I'm just going to pop that there. And had a value of 107. Now, this is a positive value, and notice that my positive value points upwards. That's important, okay? If you have negative values, they should point down. Positive values should point up. So, the next step I had was to take my gaseous sodium and turn it into the ion form of sodium. So again, I'm going to put another line. Try not to squash this together too much. We now have sodium plus as a gas, still got my half of Cl2 as a gas, and this is my enthalpy of ionization. So I've got delta HI, which had a value of 496 kilojoules per mole. So my next step then is to get from Cl2 or half Cl2 to a Cl atom. So I'm going to put another line here, make sure I've got enough space to write. I'm still keeping the sodium ion on there, so I haven't forgot that I've still got that here. Oh, and an electron. Good call, forgot to put my electron on there as well, because I made sodium and an electron there, don't forget to miss that off. So I've still got my electron and my sodium ion, and I've now got one Cl atom in the gaseous form. Now remember we said for this step that there was two ways we could do it. Now I've gone from half Cl2 to 1 Cl. So I'm going to have the enthalpy of dissociation, and it's going to equal half of 242 kilojoules per mole. I will come back and work that out in a moment. Now, the next step then is to go from Cl atom to Cl minus. Now this one has a negative enthalpy change, and remember I said that positive enthalpy changes will point up, while negative enthalpy changes will point down. So I'm going to extend my line all the way across my page, and I'm going to go down to produce still my electron and my sodium plus. And I'm also going to make Cl minus. Now in this case, I can get rid of the electron, because looking at my equation, I've got Cl atom plus an electron. That electron is going to come from the sodium to make Cl minus. So both of these are going to be in the gaseous state, and I can see that this line is going to be my enthalpy of electron affinity. Delta HEA, which is going to equal 349 kilojoules per mole. Now, my final step then is to go from these to my product. And this is the enthalpy change that I'm going to try and calculate. Now, I'm just going to turn this a little bit so we can see all of the calculation that I've done there. I'm holding it now, so it might be a bit wobbly, so I do apologise. So, if we look here, we've got an enthalpy change of formation, which points down. It's a negative enthalpy change, energy has been lost. And we've got some positive enthalpy changes. Now we should find that the entirety of the left-hand side, so all of these values, I put that there, all of those values on that side should equal all of the enthalpy change on that side. So that helps us then, because we're trying to work out this gap, but we can work out this side. So what I'm going to do here, I'm going to turn this arrow around and make it plus 411. I've then got 107, so let's start doing our calculation. We've got plus 411 plus 107 plus 496 plus a half of 242, which gives us 1,135 kilojoules. So that means that the right hand side must also equal 1,135 kilojoules. So I'm going to subtract the 349 kilojoules per mole, and that should give me 786. So if I just put that there, minus 349 equals 786. Now I can see that's a pointing down arrow, so it's going to be a negative enthalpy change. It's going to be minus 686 kilojoules per mole. And that would be my final answer in this case, and we can check it. We should have the same values on the left hand side as we have on the right hand side, and that would be our final answer. Now it is vital that you draw the Born-Haber cycle to do the calculation. I guarantee you will miss a step if you don't, and it allows the examiner to see far more easily where you have got your numbers from. So if I just take that back a second for you, and you can see that once again.